And now here we are, time for part two. We are going to be looking at a few trigonometric functions and relationships in the second part of our kind of pre-calc review, getting started with the class. So triangles. Uh, we have these trigonometric functions, sines and cosines and tangents, and they're strange cousins that we don't talk about as often. And you absolutely can productively define these things as ratios of sides of a right triangle. And that is one of the multiple correct and useful ways to think about these functions. So you can say, yes, if I have a right triangle and I have some angle in that triangle, then there's an opposite leg and there's an adjacent leg and there's a hypotenuse. And the sine is the opposite over the hypotenuse. I'm like, yes, this is true. And the cosine is the adjacent. Yep, yep. And the tangent. Oh, okay, okay. Actually, remembering that tangent is I've done a little bit of shorthand here, but the sine of the angle divided by the cosine of the angle, that is actually quite a useful relationship that pops up from time to time in simplifying trigonometric expressions or functions. All right. So we have these basic definitions in terms of right triangles, and that's great. We can use these relationships to do lots of different geometric calculations. If we're working with vectors and we want to calculate components of vectors, then we can think about the magnitude of that vector as being the hypotenuse of some triangle, and then the different components of that vector can be related to its magnitude through various sine and cosine operations. You can do that. It's great. Building off of this triangle based formalism, you can do some geometric constructions to show some relationships between the different trig functions and some useful identities that they obey. The best one, in my opinion, which is correct, um, the best one is absolutely right here. Sine squared of an angle plus cosine squared of that same angle is 1. Always true, as long as the angle is the same in both of these expressions. It actually shows up in more complicated situations where you want to simplify things. It's truly useful, and it's not that hard to remember. There's not a lot too complicated going on here. There are two other trig identities that I do also recommend committing to memory because they show up enough that it can be helpful. So one is the double angle formula. If you have sine of twice some angle, then that can be expanded out as 2 times the sine of that angle times the cosine of that same angle. Equivalently, you can convert this to a half angle formula and be like, well, what's sine of theta? It's 2 times sine of theta over 2 times cosine of theta over 2. That works just as well. All right. And then there is a cosine double angle formula. This one looks a little bit more wacky. And you might be saying, where do these things come from? Why is one of them sine times cosine? The other is cos squared minus sine squared? Like, what's the deal with that? Well, as I said, there are different geometric constructions that show you these relationships. I was digging around on the old internet to try to find a nice image that I thought represented the interrelationships between these different trig constructions. And I actually found one that I really liked. So there's a lot going on here. If you try to digest the whole thing at once, it can be a lot. Uh, Also, I do apologize. This is not particularly colorblind friendly. We've got the red and the green playing with each other. Um, but, you know, it is what it is. Even so, the labels are really helpful in breaking down what's happening here. So if you look at the black triangle in the bottom right, that triangle ABC in the bottom right corner, then you can see that we have this base of that triangle, the cosine alpha minus beta side, and that other leg of that triangle, sine of alpha minus beta. This shows you right away, okay, so if I square those sides and add them, you're doing Pythagorean theorem. That's what's happening with cos squared plus sine squared equals 1, is that 1 is the hypotenuse, sine is one leg, cosine is the other leg, and so you're doing good old a squared plus b squared equals c squared, like you've done before in previous math classes. So then building off of that, you can start to create constructions that are a little bit more elaborate. And I'm not going to talk through this whole thing because the purpose of this is not really proving all these different identities. But there is a bigger point that I want to make, which is that when you're dealing with a math problem and you have a picture, some kind of visual representation of this problem, sometimes the answer you need, or sometimes the relationship you need, isn't directly obvious from the picture itself. Sometimes you need to actually do additional work. You need to add constructions, augmentations to that image to find the relationships that you really want to build. Like taking this bottom right black triangle and then expanding it out and saying, oh, what if I grow this and I build up different components of a rectangle by, copying and flipping and rotating this triangle? This is a technique that can be really valuable in more complicated relationships. Not something we're going to use a ton this semester, but just as a bigger picture way of thinking about some of these mathematical problems. Now, as I said, though, that picture is a lot. So you might say, is there a simpler or easier way to do these things? And from a pure geometry point of view, I don't really know, actually. Breaking things down into different legs and hypotenuses, hypotenuse, hypotenuse? Okay, I'll have to think about that one, of triangles. Um, that's pretty much where it goes on the geometry side. But thinking about these functions dynamically, thinking about the sines and cosines that we encounter so often in the physical world, where you have something that is oscillating with time, that actually is what I encourage you to adopt as your default way of thinking about sines and cosines. This is one of my favorite animations in math ever. It completely blew my mind the first time I saw it. Not that I was surprised by the relationships at that point, but that someone had been clever and thoughtful about packing so much into such a small space. You could spend, well, first you could spend a few minutes just staring at this and like, you know, going into some sort of hypnotic meditative state and becoming one with the sine function. It's cool. You should try it out sometime. Also, don't do drugs. But what you could also do is to break it down into small pieces, focus on them one at a time, and see how many different relationships and interrelationships you can extract from a really rich visual representation like this. So, again, I'm not going to talk you through it, but I really do encourage you to just spend a minute with this and watch the different parts of it, see how they relate to each other, and see if you can use that to recover some of these trig relationships that I've been talking about. Like, you know, can you get that sine squared plus cosine squared always equals one by looking at these plots and how they relate to locations on a unit circle? Not doing a super in-depth review of all these things. I am assuming people have seen it before. So if I've skipped something that you think is important, absolutely ask me those questions. If something is unclear, if you want something unpacked in more detail that I glossed over, let me know. And I would be more than happy to address that in class, either with the whole class or just individually with people if you want some one-on-one time to talk about it. All right. Looking at sine functions, when you look at the sort of most general sine construction, you are going to have four key variables or four key parameters, I should say, that come into play in that sine function. So the first one, A, is the amplitude, and that is the difference between the average value and the maximum or minimum value of that sine wave. The next one is the period. So the period is the amount of time or distance, depending on what our variable x is. But it's the amount of duration between one maximum of the sine function and the next maximum of that sine function. C is our phase here. So a sine function by default, if you just have plain old sine theta and nothing else, then it's going to go through the point 0, 0. But it is more generally possible for sines to not go through the origin, but to go through any starting point to be shifted left or right from that from that origin. And so that's what C conveys is whether our function has been shifted left or right. And then finally, you can also shift the function up or down, not to change the amplitude, not stretching the function, but just translating it and taking that average value and increasing or decreasing the average that your sine wave oscillates around. And all of these things are true for cosine as well. If you took this exact same expression and just replaced sine with cosine, then qualitatively, all of those relationships would be exactly the same. Quantitatively, the difference would be that because sine and cosine are 90 degrees or pi over 2 apart from each other in phase, that your phase shift would pick up an extra pi over 2 shifting left or right, the difference between sine and cosine. You can use different kinds of units when working with trigonometric functions based on what is most convenient, based on what makes the math easier, but also based on the kind of data that you're working with. If you are doing physical experiments in the world, pulling in data, then your units of measurement are also going to influence your choice of how you express these different terms in your trig functions. So writing things out in terms of angular variables per radian. So, radians per second or radians per meter or things like that. This is the representation of a sine that you'll see most typically. So A, once again, is the amplitude. That's a scaling factor. And the amplitude, when we're talking about physically meaningful functions, the amplitude has units. If we are talking about a water wave and the water is being displaced up and down, then the amplitude might be meters, like the literal height of the wave. But if we're talking about an electromagnetic wave and we're looking at the electric field oscillations in that light, then it the amplitude would be in units of the electric field, volts per meter. If we're looking at a sound wave, so this is a pressure wave, then your amplitude might have units of pressure or list all the kinds of waves out there, but different waves represent different physical variables in the world, distances, pressures, electric fields, magnetic fields. So the units that the amplitude has tells you the physical nature of the wave. The angular frequency, so this is the frequency expressed in radians, not cycles per second, not hertz, but in radians per second. So if the wave completes one wave in 1 second, then it goes through 2 pi radians in that second, and therefore your angular frequency omega would be 2 pi. T is time, and then we have our phase shift as before. When waves are moving through space and time, so we have a wave that's propagating, maybe like a vibrational wave in a material. If you have something like an auto body panel, there's an impact, and you have this shock wave that propagates through the steel or aluminum or whatever your car is made out of, then you are going to have a function of both position and time. And the way that comes out in the math is that now we have additional variables, we have additional terms. We still have an amplitude, we still have a temporal frequency. Look at me using my big fancy adult words, but the wiggles in time of the wave, omega t. We could still have a phase, an offset, but now we also have this spatial variable, x, and then its corresponding frequency. So k, the spatial frequency of the wave, is also known as the wave number. In fact, I think for most people, the wave number is the more common name for that variable. and that is radians per meter. So that is saying as the wave moves through space, as it propagates spatially, if it as the wave moves through 1 meter of distance, how much cycle does it go through as it travels that 1 meter? If it goes through 1 cycle in 1 meter, then it accumulates 2 pi radians per meter of travel, and so k would be 2 pi in that case. If it goes through 10 cycles as it travels 1 meter, then k would be 20 pi, things like that. Wave number is a quantity that is going to come back later this semester, and it's actually very important in a lot of different areas within MSE. Everything from quantum mechanics, from looking at the physics of electrons in materials, through to, like as I mentioned earlier, vibrations, and looking at how sound and how acoustic waves travel through materials, to questions like X-ray diffraction and how do we measure the crystal structure of materials. So it's all over the place. It's something that is wave number is something that's confusing for a lot of people when they first encounter it, myself very much included. I actually remember taking my first like introductory quantum mechanics class, and the professor kept talking about K and KX and KX, and I'm like, what's the wave number? I don't get it. So it's totally normal to feel that way. You will get there. All right. For my last talking point today, before we wrap this up, I do just want to mention something that is super duper useful. It's absolutely the best. And uh, the relationship is between sine and cosine functions, so trigonometric functions and exponential functions, the two halves of our first day of lecture here. I'm not going to prove this right now. I don't want to make this video longer, but in a couple days, after we get into the calculus review, then we'll come back and show where this relationship comes from. But here it is. Ta-da! The relationship between exponentials and trig functions is right here. And this is amazing. This is just the greatest thing ever. This makes so many problems so much easier. And to try to describe the reason why briefly, because I'm looking at the clock, what I want to say is that many functions that we deal with in the physical world are trigonometric in nature, or at least have trigonometric aspects, because so many things in nature oscillate. Atoms in their lattice sites and solids vibrate back and forth. And so there's this sinusoidal nature to that motion. When we're sending X-rays through crystals to try to measure their structure, like I just said a moment ago, we're doing diffraction. And so we want to look at these waves, which have these sine and cosine components to them. But trig functions are awful because you have all these trig identities. You have to remember double angle formulas and, you know, heaven forbid you ever have to add two sine functions together. I think there's a relationship for that. I don't remember it. It's awful. Uh, so what you can do instead is you can take these trig functions and convert them to exponentials. And that is great because the properties of exponentials are simpler. You multiply two exponentials, you add the exponents. If you need to do calculus on exponentials, you take the derivative of an exponential function, it's an exponential function. You got to integrate an exponential function, it's an exponential function. So taking these problems that can get quite nasty trigonometrically if you try to do everything in terms of sines and cosines, converting them to exponential format often saves you a lot of labor. All right. I keep saying this diffraction thing. This is a TEM image, transmission electron microscope. And these are pictures of atoms. So first, let's just like stop and sit with that. These are pictures of atoms. We are at a point in society and at a level of technological advancement where we can take images of the individual atoms within solids and see their locations, see their sizes, see how they're arranged relative to each other, see defects in the structure. And that already is just completely mind blowing. But how does it work? I mean, if I wanted to talk about how TEM works, we'd be here for an hour, so I won't. But the very short version is you have your substance that you want to image the atoms within, you shoot electron waves through that prepared specimen, and the waves will scatter off of all the atomic sites in that structure. And so now you have all of these waves moving through space and time, trig functions, and they reach a detector, they hit the detector, and what you get is something like what's shown in the upper left. You don't directly see the positions of the atoms, you see the diffraction pattern of those atoms. You see where the waves have scattered off of them and added with each other. I was just talking about adding sine functions and how those waves have combined in different locations on the detector, and then you have to do all the math backward. You have to calculate where are the atoms in order to produce this pattern of scattered waves that observed. And so to do all that math, you got to know how to deal with trig functions. This is a really big deal. This is how we understand at a very, very deep level the structure of everything around us in terms of substances, in terms of materials. Yeah, diffraction's kind of a big deal. This is probably useful in other places, by which I mean this is definitely useful in other places, and we'll come back to it later this semester. But I just want to make the point it's actually really a big deal. All right, that's enough of that for now. Thanks for putting up with me. Once again, if you have questions or complaints, honestly, or I guess praise, like if something helped you, let me know that also. But this is why we have these check-ins after every video, is I really do, truly, I want to hear how it's going for you. If things are making sense, great, tell me, we can celebrate. If things aren't making sense, tell me. I'll do what I can to help remedy the issue. If something just caught you by surprise and you're like, wow, I never knew that. Cool, great. If something is interesting, you want to learn more about it, tell me. The schedule is flexible. I'm the supreme dictator of the course. I can do whatever I want. If a bunch of people want to learn more about topic, then we can make that happen. But we can only make it happen if you tell me. So do complete those check-ins thoughtfully. Tell me what's on your mind. Tell me about your experience of revisiting this material and learning new material as it comes up so that we can make this semester as effective as possible together. With that, I'll wrap this up and say, see you next time.